So again, this is the second law. Entropy is being generated. There's always an increase in total entropy somewhere in the universe. It doesn't have to be the entropy of our system. In fact, sometimes it's not. The entropy somewhere has to be increased. Okay? Now, so again, this is the second law. Congratulations, you've been introduced. This, of course, is a differential equation. I'm not assuming, as we mentioned several times, and I'll mention a few more, I'm not assuming you've had differential equations at this point. It's not a prerequisite normally for an introductory level thermo course. So let's see if we can get this down to some kind of expression that we can use. Okay? So what we can do is say, well, let's integrate both sides of this equation from state 1 to 2. So that means, so for a process from state 1 to state 2. So if I integrate both sides of this expression from state 1 to state 2, the integral of ds is just delta s, so it's s2 minus s1, is equal to, then I've got this guy, this del q over t. So I'm just going to say, well, you know what, let's just, and I'm not, sorry, let's not say equal to yet. Skipping some steps here. Let's say this is greater than or equal to. Integral of del q over t. We'll just kind of leave him right now. Again, this represents the total amount of heat transfer that occurs to go from state 1 to state 2, divided by the temperature at which that occurs. So there could be heat in on one part of the system, and there could be heat out on one part of the system, and they're just saying add up to get from one state to another, add up all the heats in, subtract all the heats out. That's really what that represents for us. Now, this is an inequality. We can convert it to an equation if we preserve the rules. So what we're saying, again, is this quantity is bigger than this one. This change is always going to be bigger than what causes the change. Now, if I say, well, you know what? Let's just say that it's equal. S2 minus S1 is equal to this integral from 1 to 2, del Q over T. Okay? But again, remember, the law itself says that this quantity is bigger than this one. So if I say that this is equal to this, I've also got to add to it the amount by which it's greater. So this is greater than this. How much greater? By this amount. This is what we call the entropy generated. And the rule here is that the entropy generated is greater than or equal to 0. Okay, so here's the rules. Here's the rules. If you have entropy generated that is positive, greater than 0, if you find your entropy generated is greater than 0, we just call this irreversible, aka normal. Okay, just about everything we're aware of generates entropy. We can point to kind of this best case scenario, what we call reversible. This is kind of the best you can get, and it serves. So what we can do is if we set this equal to 0 and solve for everything else, we're saying, well, in the best case scenario where this is 0, here's what you have, and then we compare that to what we have in front of us, what's realistic. The idea of having negative entropy generation, if Sgen is negative, this is the concept where we are destroying entropy, which to the best of our knowledge is impossible. Now, I'm saying to the best of our knowledge. To my knowledge, we have not proven the second law of thermodynamics. We call it a law, although I'm not sure that makes sense, because it's, again, we've not proven it as a law. We have a mountain of evidence suggesting that it has to be true. We have yet to observe something, to my knowledge, that violates it. So we do call it a law because we're just almost certain it's true, even though we've not proven it. So this is the idea. Okay. What I would suggest to you is, if you find yourself in a situation where you're computing your entropy generated and you get a negative quantity and it's a real device in front of you that exists in the world, and you think it's destroying entropy, do me a favor, call me. Call me. No, I've been saying that for 12, 13 years since I've been teaching this course, and nobody's ever called me, and I don't expect they ever will. But if you do find yourself in a situation, do two things. First and foremost, double check your numbers and your units. Make sure. And if you're sure you've found a way to destroy entropy, call me. Call me. We're going to be rich. We're going to save mankind. We're going to solve all the problems of the world. But call me. We're going to figure out how to do this the best way possible. Okay? All right. Again, nobody's called me yet. We'll see. Maybe somebody does. What does this entropy generated represent? The entropy generation. What does that represent? Well, we're saying here, again, that's entropy generated is not only is it the change in entropy for your system, but it also represents the change in the entropy for your surroundings. Now remember last time we talked about irreversibilities. Irreversibilities being the things that prevent a process from being reversible. If the process is reversible, that means you could get both the system and the surroundings back to their initial state. The entropy generated is what prevents you from doing that. If there is entropy generated, then I can't get both the system and the surroundings back to their initial state. Okay? If I could, if this is 0, that means I could get both this and this back to their initial state, get them back to 0. But once entropy is out there in the universe, we can't get rid of it. And so that means we can't get the universe back to its initial state. Okay? Now, with that said, that doesn't mean, and again, you've got this rule here that entropy generated has to be positive. That doesn't mean that I can't cool my system. If the water's my system, I can cool the water down and I can decrease the entropy of my system. To do that, I'm going to have to most likely put this in a refrigerator, and that refrigerator is going to remove heat from this, yes, but then it's going to kick heat into the surroundings. And as you add heat to the surroundings, you generate, or you add entropy to the surroundings. And what we're saying here, I can do that, right? I can cool my water down so long as entropy is being generated. So I can decrease the entropy of my water so long as I increase the entropy of the surroundings more than the amount of entropy decreased in the water. Okay? Alright, so here's the rules. I've already written those down on the notes back here, so hopefully you have too. But just to rehash, here's the rules. Entropy generated, normal. Entropy conserved, this is called reversible. Entropy destroyed, to the best of our knowledge, that's impossible. Okay, we've got a rigid, well-insulated vessel containing 2 kilograms of saturated water mixture. I am still on the screen. Pop here. Yeah, but I'll move it over so we can see this better. Again, rigid vessel, 2 kilograms of saturated water mixture. They give us the quality, so it's 25% in the vapor phase. Sorry, I know you're getting a glare there. 25% in the vapor phase initially. 100 kilopascal pressure inside the tank, so right around an atmosphere inside. We turn on an electronic device, some kind of electronic device that generates heat by consuming electricity inside the tank until all of the water vaporizes. Determine A, the amount of energy put into the system by the heater, and B, the entropy generated for this process. Okay, let's see what we can do. Example. Okay, givens. And what are we looking for? That's kind of our first step. Let's get organized. Let's figure out what are we looking for. What do we need? Part A, find. Part A wants to know what is the amount of electricity put into the system, right? So it's electrical heater consumes electricity, and then it basically dumps thermal energy into the device, into the tank. And B, we want to know what is the entropy generated for this process. Okay, so again, we've got water. I've got a mass of 2 kilograms. I've got an initial quality of 0.25. They said 25% in the vapor phase. It's a saturated mixture, so I use X to represent that it's saturated, and the 0.25 just tells me 25% is the vapor phase. I've got an initial pressure, 100 kilopascals, right around an atmosphere. We turn on electric heater until all the water vaporizes. So they're telling you, you could write that down as a given, just saturated vapor at state 2, or I'm just going to say X2 is equal to 1. X meaning it's saturated, 1 meaning it's 100% in the vapor phase. There's one more given in here. Pause it if you need to. It's not a number, but there's an important thing that's given here. So pause it if you don't see it, and look through this problem statement and tell me what it is. Okay, you got it? All right, it says back here, the slide will back up on me. It says it's a rigid vessel. And actually there's two things there. Maybe some of you guys caught the other thing. Did you catch? There's actually two things. Right? There's adjectives here. There's rigid and well insulated. There's two different adjectives there. The well insulated tells me Q is equal to 0. Okay? So it's adiabatic / well insulated. So here we go. So we say, all right, what tools do I have to find the things that I'm looking for? What's a good tool to find the work in, the electrical work into this device here? Well, it's an unknown energy quantity. Probably first law is a good place to start. How do we write a first law equation? Step 1, draw your system. There we are, got a tank. Doesn't have to be fancy. Step 2, draw all the energies in and out. What energies cross the boundary? Well, there's no mass. All right, I think we're going to assume, I think that's pretty safe to assume closed system. Okay. So what mass, sorry, so there's no mass crossing the boundary. What energy does cross the boundary? Well, I've got electrical work coming in to some kind of electronic device, some kind of electrical device that's generating heat inside. So it's electricity when it crosses the boundary. And it's electricity, so therefore it's work crossing the boundary. And once it gets inside, it does turn into thermal energy. But crossing the boundary, it's work. Anytime you've got electricity crossing the boundary, we call that work. First law, it's not super important whether it's work or heat. Second law, it's completely dependent on whether it's work or heat. We'll talk a little more as we go further along about how do you know the difference. Anything else crossing the boundary? Is there any heat? No, no heat. So it could be either work or heat. I don't think anything else is doing work here. Nothing else is said, and there's nothing pulling work out. There's no expansion. It's a rigid tank, so there's no boundary work. So the entire left-hand side of the first law equation says the electrical energy N is equal to then the change. This is N minus out is equal to change. It's a closed stationary system, so I think the only type of energy that's going to change is the internal energy. No change in kinetic, no change in potential. That only leaves internal energy. So there we go. Okay, so we need this. Do we know everything else? Well, we know the mass. I know the phase, and I know a property at state 1, so I most likely should be able to find U1. I know X2. Okay, so let's do this. I'm going to say P1 and X1. That's going to give me U1. That's going to be my information I'm going to use to get U1. Okay, these are my properties down here. And I also know P2. No, I don't, actually. I don't know P2. What do I know about state 2? Come back. Write down how are you going to find U2. Be ready to answer that when we come back.